Hello, Keote madam.
Yes,
Now
ma'am.
you can start.
Okay. Okay. Good evening, one and all. I, Dr. Minal Kevte, ATAL FDP committee member, presents before you this first session of day 2 in week 1 of ATAL FDP RSAML 2023, organized by Department of Electronics and Telecommunication Engineering, YCCE, Nagpur. This session would enrich you with the zeal of experiences from well-known academicians and professionals from remote sensing fields. Today, we have with us a learned expert from industry working in the area of remote sensing in the USA, Dr. Shaunak Deso from Capella Space, San Francisco, California, United States, as our speaker. Shaunak Dey received the B degree in electronics engineering from University of Mumbai, India in 2012, graduating as a gold medalist. He earned his PhD in remote sensing image analysis at Center of Studies in Resources Engineering, Indian Institute of Technology, Mumbai, India. His current research interests include polarimetric SAR, machine learning, and information theory. He serves as a reviewer for international journals, amongst them the IEEE Journal of Selected Topics in Applied Earth Observations and Remote Sensing, and the IEEE Geoscience and Remote Sensing. Now I request Dr. Shaunak Deser to proceed for the session and light up all the listeners with your expertise.
Okay, thank you so much for the introduction. I hope I'm audible. And I also just wanted to establish quickly, I'm hoping we can be as interactive as possible. So if anybody has any questions, please write it in the chat. I'm constantly looking at it and hopefully I can answer. With that, let me start sharing my screen and that way we can start going through some of the slides. Please let me know if the screen share is working.
Yes, it is working.
Okay, cool. Okay, let me just proceed with that. So,
Uh,
first of all, thank you so much for the very kind introduction. Sometimes when you come and speak at these events, people say better things about you than you think about yourself. So it's very nice. But mine, as it was in the introduction, my name is Shanak. I currently work for Capella Space and we build very high resolution expand SAR sensors. And today I want to talk a little bit about the work I've done with supervised learning on SAR data, how it is different, and more importantly, maybe how you can take away this for your own domain, right? What are the common takeaways that you can use, not just for SAR, but for any physics-based applications? So with that, a very quick introduction of me. I really like radars. I've been building radars for 10 years now.
wow.
When I'm not building radars, I walk around and sketch in cities. I don't like taking pictures. I instead like drawing, so I remember better. And I have ducks. I actually have two ducks that I take care of. Okay, so very quickly, where I work at Capella Space, and we are known for a very high revisit and very dynamic sensor. So everything is almost fully automated. So you can ask for a point of data on the ground and get it very quickly within 2 to 3 hours. But before I proceed, a lot of the times we are at these seminars and we see a lot of these applications and we think, oh, this is great. I wish I could also participate. I wish I could also do it. So first, before I start with anything, I want to come and tell you a little bit about the open data program. So almost everything I show today, it's either from UAVSAR, which is an open source data set, or will be from the open data set. There's about 10,000 images on this. You don't even have to talk to me. You can just go to this website and start downloading the data. So that way, here's some of the examples that you will see in the open data program. So this is a very high resolution picture of agriculture fields in Idaho. And you can see the individual crop lines can be noted. You can also see equipment in the farm and other things, right? And then if you want to do ship detection, there's enough images there for ship detection or port structure detection, etc. So I'll just keep this once more on the slide before we proceed. Again, anything you want to try, please feel free. Go here. If you get stuck, please email me. Don't hesitate to contact me. With that out of the way, maybe I wanted a brief idea of how many people here are familiar with remote sensing. Maybe we can have a small poll, if possible. Uh, okay. So we have two people who are saying yes, third person saying yes. So I'm going to assume, let's say, and a lot of these seem to be the trainers here. So I'm going to assume it is the experts that are aware and everybody else is not. So let's go through a very quick introduction of remote sensing. But for the people who are maybe a little bit more advanced, I'll try to keep it interesting with some history lessons also. So when we talk about remote sensing, sometimes we are asking about what the very definition of remote sensing is, right? So, for example, if you fly a drone, is that remote sensing? Yes. If you use a cell phone signal to detect somebody's motion, is that remote sensing? Yes. So I think the most wide definition usually is using any signals that have been remotely transmitted wherever, whether it was on purpose or whether it was accidentally. So in the case of signals of opportunity or smartphones, you didn't mean to transmit that information. And on the very other side of the spectrum, you obviously have major satellite missions and the ISS, which are purpose built instruments to image the Earth. So that whole spectrum is considered to be remote sensing. And perhaps what is the most interesting spectrum that is coming up these days starts from CubeSats, which is, you can say, the size of sensor that Capella is building, or Planet, or various other private space organizations. And these usually fly in the 300 to 400 kilometer height altitude range. So they are not as high as your Sentinel or NISAR or Landsat or any other mission that you would have experienced. Those are more in the medium Earth orbit, which is 4 to 500 kilometers. Then you have airborne instruments, of course. I think all of us today are familiar with UAVs. And surprisingly, if you ever wonder why people make you install all the apps, that is to get your location data so they can do some kind of marketing with it, right? So indirectly, that is also remote sensing, because you didn't mean to give away the location, but somebody sensed it from a distance. So this is, I would highly recommend going to the site gisgeography.com. There's more information. But from since we are doing a very brief overview, we can divide remote sensing into two parts: active sensing and passive sensing, right? So active sensing is something like a radar or a lidar, where you have an energy source that you send to form the picture, let's say, or data, and that energy source comes back. So in a lidar, you're sending a laser beam and measuring height. In radar, you're sending radar echoes and measuring structure. Whereas passive remote sensing is, I think, what more people are familiar with Google Earth and other things, where you have a satellite that is moving around and starting to take pictures. You take those pictures, you geocode them, which is place them somewhere on the ground, and that makes sense to you. But the disadvantage of this is, because you're not creating your own light, you cannot image at night, you cannot image in the rainy seasons, and so on and so forth, right? So there's two major classes of remote sensing. I'm going to focus more on the radar part of it, since we are going to talk more about radars. But I wanted to show you sort of a more interesting, so for even people who are familiar with remote sensing, a little bit more interesting journey of, I guess, how remote sensing came to be. So it was very common early days to have these lighter than air vehicles, right? So we call them balloons today, but it can be any shape really. And they would strap a real film camera, send it up, time and exposure when they roughly knew the balloon was at some height, and then they would wait for the balloon to sort of deflate and come back on its own, or they would cause a deflation with a rope. And when that came back, you could develop it, and you could get a very early remotely sensed map of the area. So this is San Francisco, I believe, from 1906, and it's from the University of Maryland. Of course, they have provided this data, but you can see, like, this is, it's not, we sometimes think of history as being very ancient or being very old. They shouldn't have many things, but even 100 years ago, we were clearly making maps of the Earth. So, and you can see there's good detail. I would say this is probably at like 1 meter resolution, even at least at the close end. The downside of this kind of imaging is, of course, you have variable resolution. So as you go further away from like where you are looking, the resolution drops. So that's why modern remote sensing sensors are down looking, for example. But perhaps, like, one of the more interesting parts of this history. So you have to understand the history of remote sensing is deeply entangled with the history of the military, right? The people who want images of Earth whenever they feel like it tend to also do violence and other things. So with that in mind, we will slowly proceed. As you can see, one of the first remote sensing sensors was the V2 rocket. This was in 1947. So first in 1946. So it was a suborbital mission, which means it didn't get to 100 kilometers of altitude. But essentially, it was a rocket with a film camera, and as it went over the Earth, it took multiple pictures. And when the rocket lands, you can obviously extract these films. They also had a very interesting airdrop mechanism that I'll show you next time. You can put them together, and for the first time, you can get a picture of how the Earth is, what the atmospheric patterns are. So this really started our fascination with remote sensing, right? Where the civilian population saw, hey, you can use this for a lot of things, including weather prediction, also for proving that the world is not flat, as some people on YouTube will think. The world is definitely round, and here is proof. No more questions. So we proceed to the next phase of the history. As I said, of course, people started iterating upon this. So you can see this is the Corona satellite, which is an unfortunate name in today's time. But its goal was, as you can see, it would take a bunch of pictures in orbital. It would pitch down 120 degrees and release its film canister, which would sort of be recovered midair by aircraft. So it was a very impressive feat of engineering, right? And you can see that information it collected was from its own runway. So you can see the runway and the parking apron at Vandenberg Air Force Base, which is where that picture was taken. So it's very interesting to see sort of this history, but we have come a long way from there, right? So um, to get started in the modern era, as I call it, 1964 was a project called Quill, which was one of the first. So we now know this was the first radar satellite. At the time, we thought CSAT was, because this was a secretive project. But the difference between everything I've shown you so far and what you're seeing now, this is a radar image. So this wasn't taken by just opening the aperture of a camera and letting the photons hit a film surface. This was actually pulse, receive, and use math to put it together and form an image. So you can see, even about, I want to say 50 years ago, we were forming radar images. This was not a digital system. This was a completely analog system. It was recorded on sensitized X-ray film. So it was a very interesting. We have spent a decade now trying to build a real-time SAR processor, but in theory, this was real time because it was just happening analog, right? So this was, sorry,
Excuse me,
yes,
I have one question here. How the
yes.
atmospheric errors are handled over here if we are considering the radar image?
So in this case, for example, we talk about atmospheric errors in, typically in radar, the atmospheric errors will happen at L band and above, and they
Okay.
are called. So this is because we have an ionosphere, right? So
Hmm.
if your satellite is above that ionosphere, as the like the radio waves pass through the ionosphere, at the end it's electromagnetic radiation, right? So I'm going to try and draw this out. Actually, it will be much easier. Let me see if this drawing tool works. There we go. So for
Hmm.
example, that's the ionosphere, and this is where a L band satellite is.
Hmm.
As it is transmitting, as it passes through this chunk of EM waves, right? So if you remember our classic diagram, this is the E, this is the M,
Hmm.
right? In which
Hmm.
are transversed to each other. As it is passing through a place with high amount of charges, which is basically what the ionosphere is, the E wave will be perturbed some way, right? So it will start
Hmm.
rotating off the axis that it is. Now the M wave has to also rotate because it has to keep its 90 degrees clock. I don't know if this is drawing very well, so I'm going to try and find a different tool, maybe a pen tool. There we go. So, okay, I'll draw this over, right? So this was the original E wave. It's going through the atmosphere. It's experiencing what we call Faraday rotation. So
Hmm.
this will now go off plane, right? So it is experiencing some attenuation, obviously, because it's losing energy to the thing that is passing, but it's also now shifting in polarization. Now, for imaging purposes, this makes no difference whatsoever, right? Because the polarization is not easily detectable in the radar imaging that we do. But what it is detectable in is when you start taking ratio of two bands, right? So you're taking HH versus
Hmm.
VH. It
Hmm.
will not have the same characterization. However, this particular image that you're seeing here is an aircraft, right? So it is flying much below the ionosphere. This is flying 2 or 3,000 feet above mean sea level, whereas the ionosphere is somewhere close to 50 or 60 kilometers. So for this particular case, the motion of the aircraft is probably going to affect a lot more. than the ionosphere. But yes, in general, when we talk about especially L-band radar imaging, yeah, you will have some effects, and there are techniques called Faraday rotation correction, or FEC, forward error correction, that we sometimes apply, and you can use that to somewhat recover the phase, because the troposphere is a pretty known object. And also, when you're imaging in the day, the ionosphere is disappearing. When you're imaging at night, there's ionosphere. That's why you can bounce radio waves. So if you have two images, you can difference them and find out what the ionospheric effect was. So there are
Okay.
techniques, but yeah, of course, there is, I will say there is far less, and I have a slide for that next, so let's get to that.
Yes.
But
Thank you.
before, no worries. But before, and please, everybody, please unmute and ask questions. I'm very happy to answer questions. We have more
Yes.
slides in this present. Yeah, sorry. Go.
Yeah, yeah. I have one more question, that if
Yes.
dense cloudy area is the weather is there,
Mhm.
then again the capturing the signal through radar would affect the image or signal.
Yes, that is actually very interesting. Let's go through some images
Yeah,
and then I'll talk
definitely.
about it. But
Yes.
that's a very interesting question, and it is, turns out there is no. I mean, there's one simple answer, that radar waves pass through clouds,
Yeah.
but there is a little bit more nuance there. But yes, please, everybody, I'm watching the chat very regularly. I hope the presentation is not interrupted when I watch the chat.
Yeah, yeah, definitely.
Okay. All right. So again, as I said, we have lots more slides, so please ask questions. We'll not go through this presentation totally. But this is a more recent radar image, so you can see in about 60 years of development, we have come a long way. So this is also an airborne image. It was acquired by the DLR, and this is a 1 meter resolution image. So I think it's pretty rare for people to be able to see a 1 meter image. Some of the things that you'll start to notice, it's very odd how the planes and helicopters look in radar, because modern jet fighters are designed to be radar avoiding. So a lot of the times you will not see like an aircraft shape, and we'll see this more as we look at some more images. And then this is further perhaps an improvement. This is a 25 centimeter image from the Capella space sensor. So you've already seen some high res images in the previous slides, but you can see some of the further improvements from that last image. You can start to see parts of the oil tank, if you can see there, right? So you can see that, sorry, let me also try to mark without obscuring the image. Okay, so if you look at that, you can start to see things like, you can see the lid, the bottom and the top of the oil tanks. And if you zoom further in, you can start to see little studs on it that they use for lightning conduction. You can see details on the ship, and so on and so forth. And one interesting thing to notice, if you see, there's a lot of variation sort of in this marshland area. I want you to keep this in mind as we go to the next slide. And we talk more about the question that we were asked, right? Which was, what happens when there is clouds? So this is typically what you see in most remote sensing textbooks as something called the atmospheric window diagram, right? And perhaps, we were asking this question of what happens if there is clouds or dust. So typically in the atmosphere, there's various reasons that a signal will be impeded, right? There is a big window, if you notice here, where there is absolutely no transmission, like between the wavelengths of 100 micrometers to 1 centimeters, everything is blocked. And this is very much in the near infrared and ultraviolet band ranges, which is why when you go out, you don't get skin cancer immediately, right? Because the atmosphere is blocking most of the solar radiation. But beyond that, you'll see these like spikes here. By the way, how to read this graph? If everything is blue, nothing passes through it, right? But if something is white, then it has full transparency basically. So I hope that is clear. But as we go through this, you'll see there are some atmospheric windows. I'm going to point out some of them which are very interesting and which are very used for remote sensing. So this particular window you can see at the 10 micrometer wavelength. So this is near infrared, and you can see there are certain windows through which you can see it, right? And the reason for these particular windows are useful is because when you see images of like clouds, or when you see images of heat transfer on Earth, that's what you're trying to see, right? And also trees stand out very much with something called NDVI image, which is you're taking a ratio between the near infrared and the red band, which is further down here. So you're trying to find out, okay, what was the ratio of infrared to red, and that will tell you if the plant is healthy or not. Some of the other more interesting atmospheric windows, of course, we know is the full color spectrum, which lies somewhere here. So we can all see RGB as we go through it. But as you start to go sort of in this higher frequency range, right? So as you go in this microwave range, everything from K, X, C, S, and L have very high transmission through the atmosphere, which means almost nothing in the atmosphere really blocks it. Not water vapor, not clouds, not aerosol, right? But I said the reason that question that we asked was interesting. So according to this diagram, the answer is radar goes through clouds, radar goes through fog, which is true. But the part of which where it is a little bit more nuanced is, so if you imagine like something is going through the clouds, right? I'm going to try and draw a very horrible cloud diagram here. Okay. So you have clouds. The radar wave will pass right through the cloud, no problem, right? But these clouds are also usually bringing rain or precipitation, and RF cannot pass through water. So while you will see an image through the cloud, you typically will see like a footprint on the ground that is, it looks wet actually. And we can probably search for this and like I would encourage you to look for it, rain in radar. It's a very interesting topic where you've gone through the cloud, but you're seeing the actual rainfall on the ground. So it's not like you still have 100% visibility, but you have more than optical for sure. I hope that answers the question. If not, I can try to find an example like that and show you
No,
afterwards.
yes, yes, it is clear now.
Yeah,
Thank you.
no worries. Um, One question, I've been talking about synthetic aperture radar. Synthetic aperture radar. We all understand what a radar is, right? You pulse something, you get something back. So what is synthetic aperture? So if you just simply pulse something on the ground and got it back, you have to have a very, very narrow antenna beam width, which means you have to have a very large antenna, right? So it's a very easy visualization, which I'll try to draw on the top of there. So if you have a small antenna, you have a big beam, right? But if you have a long antenna, you can have a very narrow beam. This is just basics of electromagnetics, and we cannot do anything to cheat physics, right? So let's say with a practical limit on what we can launch into the air or what we can fly on an aircraft, what we would achieve is something like this real aperture radar image you see here, which is 5 by 14 kilometers, right? Because even a 1 degree beam width on the ground, in the air, when you go so far on the ground, will cause a very big footprint. So I think it's very interesting. Again, it's a historical imagery that we have. So the same radar, when you take it and you apply something called a synthetic aperture radar technique, you can get a much higher resolution image. You see, you go from having kilometers to meters. So it's a massive difference, right? And you can see the shapes are roughly the same in these two images. It's not like something is vastly different. This lake here is this lake here, right? But the resolution just improves so much. So how does it improve, you may ask, right? So let's take a simple example. So we said we couldn't send an antenna that was so big in the air. But what if we send a much smaller antenna? I'm going to find a different color so I don't confuse you. Let's say in the blue, right? So we have sent a smaller antenna, but this antenna is moving. So can you see intuitively, eventually, if the antenna is moving and you're recording all the data, you should be able to simulate the effect of a much longer synthetic aperture or much longer antenna. And that is one of the beauty of like the math that comes out of synthetic aperture radar. This is the very shortened version. Of course, there's more complexity to this and there's lots of trade-offs. But I think I wanted to establish intuitively, this should make sense now, right? You have a small antenna here, you're pulsing to the ground and you're taking overlapping pulses. So this one, this one, this one, this one. And now by constructing this information from overlapping pulses, you can oversample in some ways and come up with a pretty good image, much better than what you would have with the real aperture radar. And we'll look at a little bit more details of why that happens, and I have a video to show. But one of the most interesting things that come out of this is that your synthetic aperture resolution only depends on the antenna and it's directly proportional. So the smaller you make the antenna, the better the resolution, which is a result that you don't quite expect, right? Because the more small samples you take, you're oversampling, so you get a better idea in very basic signal processing terms. But I said I have a video to demonstrate, and I do think a video is the best way to demonstrate this. So give me 1 second to play this video. So as you see, the colors that you see in this video is a red blue Doppler shift, right? So there is a point on the ground, green. So relative to where that point is, initially the satellite has a blue Doppler shift, which is shifting over, and then as it's going away, it's having a red Doppler shift. So that's the image. And you can see sort of in this animation, as the sensor goes over this point, right, you have a blurry image, but you get more and more and more samples, and you're starting to form a better and better radar resolution. So if you see, it's not a, like, you would expect we're scanning the ground, so it should like paint the ground, but it's not a question of painting the ground. It's a question of the whole antenna beam width contributing to form a pretty high resolution image from where we started, right? So I'll play this over once again so you can see. Look at this. This is a unfocused and blurry image, right? As it's getting more pulses, you're starting to see more detail in the azimuth resolution. Azimuth means along the line of the satellite, so that is azimuth. And this is range resolution. Range is caused by the bandwidth available. So if you notice, the resolution in the range doesn't improve at all. It's just fixed by the chirp. The resolution in the azimuth improves a lot. Uh, and yeah, this is a very confusing thing, and it takes some time to understand, but I hope with this animation it becomes a little bit easier to follow. If you want to see this animation again, you can go to the NISAR website, which is the NASA ISRO Synthetic Aperture Radar, and they have some more details in text form and this animation. So if you're confused about how this image forms, there's another way to see it. And sort of, I wanted to leave this animation slide. This is from one of our marketing slides at Capella, but you can see just how the imager works here, where we are supposed to scan certain portions of the ground based on what order, right? So you will have attitude control of the satellite, and then the yellow thing that you see is actually downlinking the data. So that is a sequence of typical satellite operations. You've taken 2-3 collects, your flight data recorder is full, then you want to find a downlink location and downlink. Uh, a lot of the movements in this animation are obviously marketing animation, but the principle is the same, right? With that, I'm going to pause for a second and ask if anybody has any questions, because we are sort of halfway there and I want to start getting in the more applications. But if you have any questions, let's clear it up. Okay, I see a question. What is the expected sampling rate for RS images for better resolution? It depends heavily on what the modality of the sensor is. So for example, the best resolution you can get out of optical sensors is about 15 centimeters in worldview, the latest worldview, right? So this is basically the physical resolution the camera is capable of. Typically, what the satellite providers will do will deliver you 2 times oversampling, right? Because I know that I cannot discriminate with my like physical sensor anything more than 1 meter, so I should give you half meter. So I'm covered by the Nyquist frequency. Now with radar, it is a little different. Radar is actually, and of course, with the optical sensor, the common like physics applies. So if you reduce the height of the sensor and you're able to focus on the ground correctly with that telescope, then you improve the resolution, right? So that's why UAVs will have much higher resolution into the centimeters, like 2 or 3 centimeters. How many maximum bands can be covered in SAR? Okay, so we'll talk about the bands and that concept a little bit, but yeah, sampling rate for SAR actually doesn't depend on the height. It only depends on the bandwidth and the synthetic aperture antenna. So whether you do from space or from the ground, you're about to get the same. Okay, to answer the second question, bands. So typically when you think of optical remote sensing, right? And let's go use our fancy diagram again. You think of bands. You say, I can measure, let's say, infrared band here, then I can measure the green and the red. In case of SAR, you're mostly thinking of frequency, and most SAR sensors, actually all SAR sensors that are flying in space and most sensors that are flying in the air are single frequency. So they're designed to produce C band or S band or L band. What changes is what bandwidth is available to them, right? So at X band, I might have a lot more bandwidth in the RF spectrum than in the L band. And if you look at the resolution in the range direction, that purely belongs to bandwidth. So the equation for resolution in range, so in meters, is 2C by B. That's it. And of course, there's some multiplier for the windowing function, but I'm going to ignore the complexity. It's like if you want to do easy physics, right? So ignore the drag. So ignore that part. So yeah, all you're looking at is 2 times the speed of light. So resolution of any radar sensor is very easy. 2 times the speed of light divided by the bandwidth. The bandwidth is usually measured in megahertz. So for example, to get 0.5 meter resolution, you need a 500 megahertz bandwidth. To get 25 centimeter resolution, you need a 750 megahertz bandwidth approximately, and so on and so forth. So if you can find So there's two governing bodies here. One, if you can make a radar that has a higher bandwidth, which is not an easy task, you can get a better resolution, of course. But the other part is you should be allowed to transmit that bandwidth, because typically X band and L band and S band, these are very close to cell phone transmitting stations, let's say. So you don't want to interfere with people's other transmission, right? Because at the end, radio spectrum is limited. So yeah, in theory, you could get an infinite resolution if you had a 6 gigahertz bandwidth, but you're limited by hardware. And typical intensity resolution. So that's a very interesting question, actually, because one of the things that I said we should notice, let's take this example. You see a very high dynamic range. Like the area that you see in the water, this is for the Capella radar. This depends very much on the radar. It's called noise equivalent sigma 0, which is what is the absolute floor you can measure, right? For us, it is minus 20 dB, right? And then you'll see something super duper bright, like let's take this urban area, for example. This is going to be closer to plus 5 dB. So what you have is about 25 decibels of dynamic range, right? And of course, we all know decibel is in log scale. So like 3 dB is double the power, right? So you can imagine if this is at minus 20 and this is at, just for easy math, let's call it 0 dB, right? Or minus 2 dB even. So that is 18 dB. 18 dB divided by 3 is 6. So that is 6 into 2, which is 12 times more power than the dark part, right? So there is a huge dynamic range typically in radar. And all of these images that you're seeing presented, they have been log compressed in some way. Otherwise, it's very difficult to see. If you open a raw radar image, you'll only see darkness. And if you adjust your histogram to see targets, you'll only see bright targets. So we are compressing a huge dynamic range. I can try to represent that here, right? So here we have 20 dB of dynamic range. When you take the log transform, it tends to shrink a little bit. That's how you can represent it 0 to 255. So yeah, when you open a raw radar image, unlike a satellite image, it typically is in float. So float 32 is the most common format to, for example, in the radar image. So we use the dynamic range of whatever float has. And I think we have another question here. Can we use band ratios for image analysis? Yes, band ratios work a little differently in radar, and I'll come to quite a bit of detail about that. So we'll go there. It's called polarization for instead of bands, for example. And is there any loss of information? Yes, if you anytime you go from having a huge dynamic range to having to compress it down, you're going to lose some information. So um, I I would encourage you to download this data. This particular scene is available on the Capella Open Data. You can download anyone and just try to view it in ArcGIS or something. You'll realize just how much adjusting you can do before, obviously when you bring it down, you're compressing the data. So if you look at the raw image, this area would also have like a gradient, for example. Okay. And I guess this is so far the questions. Please send me a question and interrupt me anytime. But now I wanted to sort of go on to the very brief introduction to machine learning part of it. So because I wanted to give a one slide information, so I put all this information in one go. So AI is not as new as we think. I think everybody knows that. In 1940, McCullough and Pitts worked on the first model of the electronic brain, or the neuron as we call it. So they demonstrated they could learn and, nor, XOR. So once you demonstrate that, I think we all know from computer science, you can build anything, right? It's just a question of throwing more neurons at the problem. There were some other like technical problems that were solved. One of the harder problem turns out is the XOR problem. So if you try to think about it, draw like these conditions for, so let's say this is, I'm going to mark over this diagram so I can explain this. So let's say this is 0 and 0, right? Input is 0, second input is 0, 0, 1, 1, 1, and 1, 0. When you draw this like logic diagram, it's very hard to draw a straight line that successfully does that classification. And the trick that Minsky and Pepper discovered is called the projection theorem, where if you project this to a higher dimension, you can basically classify it. It's called the kernel trick. You might have heard it's commonly used in SVMs, right? But moving more towards like the modern era, sort of through 1990, it was the work of Hinton and his student Jan LeCun, and then Wapnick and others that like brought on this modern era, right? And this is a fascinating story. I'll point a link to it at the end. But essentially what started happening is we started realizing we went from like using SVMs very heavily that use this kernel trick and were mathematically very efficient to the more modern era of AI where we are basically just all using deep neural networks, right? And if you have any questions about this or want to hear more about this introduction, please ask me. But I just gave you a very quick overview of this AI as it has passed. I wanted to show you two very quick. So this was the original perceptron that I was showing you. It was called the Rosenblatt perceptron. And you can see it had to be a physical wiring, right? So if you're asking why has AI suddenly taken off, it's because computing power has improved suddenly, right? Like people are playing video games, so there's more GPU capacity, which means there is more AI. No fundamental improvement in technology has occurred except I guess you don't have to wire things by hand anymore. uh, and yeah, this was the paper I sort of spoke about earlier that showed for the first time it is really hard to do XOR functions and how it can be overcome, theoretically at least. And I would highly recommend reading this book, Perceptrons, if you're very interested in AI and you want to see the history of it. This was, as I mentioned the student Jan LeCun after some time. This was when he was working for the US Post Office, or he was working for AT&T Research doing a project for the US Post Office. And this was one of the first examples when neural networks were actually shown to be practically useful. All of you may know this as the MINS dataset. So if you ever wondered where the MINS dataset came from, it was from this paper and this research all the way back in 1989. Probably many of you were not even born then. So um, but essentially what we have gone is gone from having a 3 neuron network that he used here to like several million parameter network that you see with ResNet and all of the modern ones, right? So I know I've gone through very quickly the history of AI, but I feel like you probably don't need to know the history as much as you want to know why. So before I proceed, I did say the story of Geoffrey Hinton is very, very interesting. I'll quickly go over the story because I think it's a very inspirational story for us all. This man basically was running out of funding at University of Toronto. He believed in his work in deep neural networks, but obviously it hasn't taken off. Computing power wasn't there. It wasn't working. So he moved from his original university to the University of Toronto, took up a Canadian government scholarship or fellowship, worked for 6 years on it. And of course, today, you know the AI revolution that has happened around you. And Geoffrey Hinton obviously is one of the big heroes of it. So I would highly recommend this Chronicle article. I think it was aptly titled The Believers. And yeah, you should absolutely read it. It's a wonderful read. But the reason I wanted to avoid talking too much of the history is because I wanted to go to very practical parts of it, right? So for me, AI in machine learning is a tool, right? So it's the same tool as using statistic, as the same tool as manually labeling something, taking band ratios. So we should use it as a tool. Roughly in machine learning algorithms, there are three big categories. They're called unsupervised, supervised, and semi-supervised. This is weird and we'll talk about it later. But unsupervised is when you have a lot of data, right? So X, and you need to predict some labels Y, but you have no human labels for it. All you have is this relationship. And just by statistically observing this relationship, you can usually make a pretty good prediction. Some of the examples of this is k-means, for example. And k-means is a wonderful algorithm to draw graphically. And I hope all of you will also follow along. I know maybe you can't speak with me, but like, let's draw some red triangles here, right? And let me draw some green circles here. Can you tell me a way of separating these red circles from these green, red triangles from green circles automatically? So let me actually ask the question in a little nicer way. If I draw this X here, what do you think? Is that X possibly a red triangle or a green circle? You could start typing it in the chat. Quick question. Blue, is this red or is this green? Just type R or G in the chat. Let's see. Red. Okay, we have one red triangle. Almost everybody says red. And I think we can guess why, right? Because as a human being, we said that the distance of this blue cross is closer to this red than this green. And that's basically how k-means operates. You take an unknown point in the space, let's say here, then you compete and you can do this manually also, compute the distance to each of this and then sum it over. So sum of whatever x dash minus x the whole square, right? And then you do that, you subtract it from the distance of the other group. So I'm calling it y for convenience here, right? So distance from this one, and whichever one it is closest to, it wins, right? So yeah, then you can say this is closer to green, so this is in the green circle, and this is closer to red, so it's in the red circle. Of course, if you did this individually, it would be very compute efficient. So k-means finds a very interesting trick to do it, but that is the basic concept of any machine learning algorithm at the end of the day. No matter what, whether it's a neural network, whether it's k-means, whether it's unsupervised or supervised, what it is trying to do is go from a data space that you have to some latent space where the data is separable, right? Hopefully that makes sense. So the unsupervised techniques are very interesting because you don't have to find human labeled data. I think if any of you have tried to do anything in deep learning, you've realized without labels, you're not going very far. But that's not true. You can go quite a distance. You can use Markov models, autoencoders, clustering to do a very wide variety of tasks. I wouldn't wait for labels. But on the other hand, it is true that one of the more impressive uses of AI that you see, everything from chat GPT to stable diffusion to the kind of classification that you see around it, almost all of it is supervised. There is an army of human beings that are providing the labels. So you look at the data, you look at the labels, you combine them with some math equation to predict whether or not a certain thing was in a class or not, right? And this is an easier problem to solve than unsupervised, because obviously you have the labels and you're just letting the machine find the underlying statistics. Semi-supervised is a hybrid version of that. We should not talk too much about it right now, but if we have time at the end, I'll show you some applications of it. But now, so I'm going to start with some applications of machine learning and remote sensing. If you have any questions so far, something's not clear, please ask. And after this, hopefully we can go at a faster pace and like cover a few applications. I'm going to assume no, because I was looking at the chat. Let's go look at some unsupervised application. The reason I want to show you the unsupervised applications also is because that will typically be where you can start off tomorrow, right? You can download the data and you can do something. And I also want to show you, not like all of this is not like some unimpressive application, right? Uh, so a lot of unsupervised applications comes from deeply understanding the radar image. So earlier I was showing you a red blue Doppler shift that was happening as the radar image was being computed. I hope you remember that animation. So now if we go find the Doppler shift in the image and then color code it, you get this very wonderful record of like anything that has moved, you see. So we know anytime anything moves from basic physics, there's a Doppler shift. That was the wrong color to draw in. Sorry. Hopefully you can see this arrow. So you see, there was these boats. So the boat that hasn't moved is still here, but the boat that has moved has formed this wonderful rainbows like arc, if you can see, right? And similarly, I'm going to zoom into some things that will also show off the high resolution part of this image. So sort of zooming into downtown Shanghai, you can see that the echoes from one part of this came. Sorry, I should not hide the thing I'm trying to show. The echoes from one part of this, I'm going to do it in green and hopefully you can see it then. Do you see this area? The blue echoes came from one side of the building, but the red echoes came from another side of the tower, except on this dome shape. So if you see, the dome has the red first and the blue later, and that is probably because the radar signature got trapped in the dome for some time. There's multiple reflections, right? So just from physics, you can tell a lot about this radar image. This is actually called a colorized synthetic aperture image, and it is very useful for finding motion detection at everything. So sort of the next step for this is you find colors, and anywhere there is a color, there is probably motion, right? So I'm going to zoom further in so you can see actually. So you can see there is some structure in these towers that traps the radar waves that causes that delay, whereas the other side is not delayed. So I guess the lesson that I'm sort of trying to give you here, the takeaway lesson, is that if you understand the physics of what is happening, there's a lot you can do with unsupervised learning. And there are several applications where the physics are important, right? Like if you see biomedical ultrasound, you can't just make a prediction without a reason. There has to be a reason for that to happen, right? So this is one of the cool applications that is completely unsupervised, totally from the physics of the radar, right? With that, I'll move on to the next one, which is, for example, like co-registration. So this is another problem that you typically have. The reason this image looks green and pink is because I've taken two separate images of two separate days and laid them on each other. And one of the things that I guess is not immediately apparent, the satellite doesn't maintain a very smooth orbit. I know we say it's in space, but you have to remember you moved it around a lot to take different images, right? Sorry, my drawing is really horrible there. So because of these perturbations, it's actually following a non-ideal trajectory, or what we call a non-ballistic trajectory through the air, right? So if it's not following a ballistic trajectory, it's very hard to actually predict where it will be or where on the ground it is looking. And we come very close. You can see this is only 1 meter apart, maybe, or maybe even less than that, because this image is 25 centimeters and what you're seeing is a wall right there, if it wasn't clear. So you come very close, but it's not ideal. What you want to do is match the two images and register them, as you see on the right here, right? So again, all of these techniques don't require unsupervised machine learning. What we did is we actually trained an autoencoder to match different parts of the image, and using the score of the autoencoder, we shifted the image heuristically till the image lined up. And you can see, like, actually it's probably the most apparent on the roof here. You can see those poles didn't line up before and the poles line up now, right? So that's a big improvement if you're trying to do something like time domain analysis, etc. And a lot of this is running in a massively parallel way, so that way you're not even spending that much compute time. So a lot of this would be very hard to do in a supervised manner, but of course there's a powerful application of unsupervised. And I wanted to leave like the raw image to show you just how much it changes. So to the left is before registration. You can see it's also kind of blurry. In the process of registration, it becomes a little sharp, a little crispy, and you can see that this arc is roughly in the same place in all images, right? Whereas here it's clearly jumping around, you can see. Anyway, so this is one example of where you can use the physics of this process. So what do we use? We know that the two images will be roughly similar, given that nothing on earth changes that much. Like a car will move, but major structures will be very similar. So we then use this image similarity algorithm to go find shifts and then use that to match the images. But maybe one of the more interesting applications of something unsupervised is change detection, right? So this is a very common application, as you can imagine, in remote sensing. What changed on earth, right? Like a big part of remote sensing is not just for us humans to look at the images, it's for something to automatically alert us. There's a landslide, there's an earthquake, a building got constructed or destructed. So you can, if you follow along these steps here, so you're taking these two images, you're doing some kind of a filtering, right? Because if you notice, the radar image has a lot of like what is described as salt and pepper noise. It's actually called speckle, and this is not noise, it's part of the imaging formation. This is also true for ultrasound images. Because these two mediums are coherent, they form speckle in the image. So you do that step, then you do the co-registration I just showed you, and then you do some kind of metric computation, right? So now this is a completely unsupervised and from statistics. If I have this image and I have this image, right, what is the difference? If you think about it, if I start drawing the histogram of this image, there is no data except in the brightest bin, right? I'm going to use a green pen to indicate this other image, right? But here there is some dark pixels and then some bright pixels. So clearly I can detect the two histograms are different. That means if I pretend these are like PDFs, right, probability distribution functions, which we all long ago studied in school, I can come up with a PDF that fits this, and I can come up with a PDF that fits the other. And now you can use regular distance functions that you know from math to find the distance between the two, right? So let's take a look at that. So you can see this is image 1, this is image 2, sort of going window by window, block by block, so that's why it looks so blocky. You can see, you can easily detect the change in that image, right? Is this clear so far? Now, the interesting part, of course, is not just where is the change, but to threshold it and make some automatic decision on this, right? I know this equation is long and complicated, ignore it, right? The main idea is you're trying to find difference between two histograms. And of course, you can use all of the distance functions that you have studied and not studied in school, from Minkowski, Canberra, log ratio, total square error, Cauchy-Schwarz, chi-squared. I think this one is more popular as the student's t-test, if that's something you remember from statistic. So all of these distance functions are available. The idea is, how do you threshold it, right? I said earlier I'd show you how log compresses an image. So this was a distribution that we had initially of those distances. We want to compress it so we can threshold it. So once you do that, you can then find the 2 and 98 histogram clip, right? There's clearly the histogram changes in this orange image at some point. So if you then assign them to positive change and negative change, which is construction and distraction, you can get a very fast algorithm that like very reasonably finds the change in two images. I haven't trained this algorithm manually. I haven't supervised it in any way. What I've done is understood the physics of the process, a little bit of statistics, and just applied it, right? And if you apply this over time, you can see some very interesting patterns. So this place is Djibouti. It's a Chinese naval base. So you can see, of course, you expect activity in the port area. But notice, if you look at the port area, there's a lot of material collected that is gone and deposited in this construction yard, which is then at a later date used to construct this runway, right? So I could say a lot about this area just from the change stack. And you have to remember, none of this was a supervised or neural network or manually labeled, right? So you can already do a lot of impressive work just from unsupervised images and open source data. But sort of to go to the next part of this presentation, we can do a lot more with supervised applications. And that's what I wanted to show here and indicate here, right? So before we start this section, again, any questions so far? Quickly looking through the chat. Okay, so we don't really have that many questions so far. We're going to go into the supervised section. I just also wanted to get a brief idea of like, would you like me to slow down and explain more the machine learning parts, the radar parts? Is the pace okay? Okay, I'm going to assume we're going okay and we'll proceed, right? So this slide should be very obvious to everybody, but I still wanted to put it to just show how much more data we are getting back. So one of the first radar satellites that was available for commercial use was NVSat, right? Over its life, it collected 1.7 terabytes. I'm sure some of you can fit this in your phone now, right? But as time went on, you see, this was the 1990s. As time went on to the early 2000s, you can see the data volume is increasing, but the data volume has increased massively. Like the Sentinel mission has collected 1.2 petabytes of data. This is not something a human being can over its 7-year lifespan. And by the way, it's still going, right? So this is expected to grow further. And worse than that, the NISAR sensor that will launch next year, early next year, is expected to collect about, I want to say, 2 terabytes a day. So if you multiply 2 terabytes into 365 into 7, I think you see it's a lot bigger than 1.2 petabytes. So we are in, with as technology has improved, we are collecting ever increasing amounts of data. And no human being, this plot, as you can see, is from 2015. I haven't updated this plot in a forever, but you can imagine, like, no human being can look through all of this data. Second of all, maybe you don't want to look through all of this data, right? Like, as a human being, you would rather do the thinking part, not the boring, like, oh, I'm looking for a ship. Oh, that's a ship. And even worse than that, typically, if you've noticed, human beings who do repetitive tasks are not very good at doing those repetitive tasks. Like, if you had to sit and label ships all day in images, you will start missing some. You will start becoming faster and sloppier and other things, right? So that is the scenario we want to avoid by using or leveraging machine learning. So that I did want to give a brief overview of deep learning, even though I think it should be very common to most people now. But just to go through the history of machine learning and the algorithms that we spoke about, a lot of the algorithms that you saw before, like you can always make a rule-based system, right? If I say NDVI is greater than 0.8, it is tree, right? NDVI less than 0.8, it is water, and so on and so forth. So this is how a lot of quote unquote intelligent systems did operate. You hand design some of these features based on observation, your geography, etc. But then we started moving away from that because it is tedious to bring global solutions for that, right? Then we moved to what we call classic machine learning, where you have input data, you still have hand design features. Like somebody is going and saying, extract texture from the image. So I'll give you an example of this particular case. Are you all familiar a little bit with image processing? I hope I'm image processing. Yes, no, very quickly. Yes, okay, very good. So we can just go with some of the example of these stages, right? So when you go from input, which is your image, you can go to some hand designed features. So if you remember from image processing, you can take something called Laplacian of Gaussian, right? Or depth of Gaussian or some of the other ones. Then you can take some textures like SSIM. You can compute the gray level coherency matrix, GLCM. So all of these things are extracting something about the image. Like this typically extracts the edge, this typically extracts structure, this typically extracts texture, right? You're taking all of these metrics and then giving it to a machine learning. So you still had to do some thinking as a human being, but at the end the classification was done by a machine, right? But this is getting, like, this is a really good strategy, except it might take you 2 to 3 years to develop something that works for your application. And maybe the application changes, maybe the image changes, maybe the camera changes, suddenly you have to go redevelop all of these, right? What window size of Laplacian of Gaussian you want to use, what window size of shape similarity you want to use, is shape similarity still good? So obviously, you can imagine, as companies were trying to push machine learning into production, they didn't want an answer of, oh, the camera changed, so now we have to spend 2 years doing R&D, right? So that's where we started looking at this thing called representational learning, and this started becoming more popular in the 2003 era, where yes, there are some features, but you would pre-calculate a very big set of features, right? Like every information feature you can think of, GLCM, shape similarity, HOG, which is the Haug transform, right? Laplacian of Gaussian, edges, first dimensional differentiation, second. So you have like hundreds of features, and you use the machine learning to reduce that feature set. So if you have hundreds of features, you're using it to reduce it to like maybe 16 features. You're compressing information, right? And then you're passing it to a traditional machine learning algorithm to get your output. Does that make sense? So you're going from 256 features to 16. This will be very common also to people who have done sort of like hyperspectral imaging. You have 256 bands. All of that is not useful. So you take a PCA, right? You compress the data up front. So PCA actually was a very common dimensionality reduction strategy also, along with SVA. Now, once this era sort of ended, yeah, if you're already pre-computing all of these features, then why don't we take this to the extreme? Why don't we have the computer find the features it needs and then compress itself? And that is where we have entered this era of deep learning, right? So in deep learning, and I've shown you here with a very simple diagram, I would also encourage reading the paper by Ziegler. I think it was very interesting. But you see, in this very bottom layer, what you have is visible pixels, right? You have this image, basically. Now, if you construct a neural network such that one part of the network is just taking gradients, one part of the network is looking for edges in this direction, right? You start to get these set of features, let's call it, which can identify, like maybe this neuron can identify gradient. So this is a plane area, right? So neuron 1, neuron 1. This neuron identifies horizontal line, so her shoulder, neuron 2. This neuron identifies vertical line, so like her face, 3, right? I'm saying identifying because it's the English sense. It's not actually identifying. It's just computing some numbers, right? Then it's passing it on to the next layer, which is starting to combine things. It's saying, hey, if there is a horizontal edge and if there is a vertical edge, it might be a wheel actually, or an eye. If there's only smooth area, it might be the background, right? And then you start to go into this higher level of complexity where it knows object parts. So it's like, oh, this is a wheel, this is a face, this is a post. And obviously modern machine learning has many more layers, right? So it finds subtle relations between objects before it comes with the output. Here, if you noticed, your only effort was providing the image and providing the label. The rest the computer did. And this is the big allure of deep learning, right? If you can provide the labels and the images, in an ideal world, the computer will learn the outputs themselves. So that is basically what deep learning is. And if you read the definition, it's about the same. Allows for the algorithm to learn complex abstract representations from a series of similar concepts, right? So Hope so far it is clear, but that was this like a very high level introduction to what deep learning is and why it works. What I want to get back to is, of course, how to use it in remote sensing, because that is sort of what we've all come here to think and try to understand. So earlier there was a question about bands in radar, right? So as you can see, there is no real what do you call it? There is X band and L band, and there are two different frequencies, but that's not coming from the same satellite. You'll rarely have the same X and L band images together, right? That only happens with special sensors. What we do have is something called polarization, right? So all of you hopefully have experienced polarized glasses at least, or maybe you have done the experiment in the lab where you rotate a filter and the light changes. Okay, I'm going to assume all of you have experienced polarized glasses. If you haven't, borrow one from anybody that has it and then just put it on. Look at something that is reflective, right? Like water surface, window, glass, and try to rotate your head. What you're doing is you're changing the orientation angle of your receiver, which is your eyes covered by the polarizer. So when sunshine, or when sun shines rather, it's sending out all polarizations of light, right? But when it's reflecting off a window, only the horizontally polarized light is coming back to you. So you tilting your head starts cutting it off, because most sunglasses are also horizontally polarized. Similarly, with the water surface, only vertically polarized light is coming to you. So that is one of the things. Polarization, of course, works the same in light as in radio waves. It's an electromagnetic wave property. The difference is, in a radar, in light, there is no real way to create polarization. And if you remember your 11th, 12th chemistry experiments, you have unpolarized source of light, L. It passes through some filter, F, and then it is polarized at 45 degrees, right? And then you pass it through glucose, and then you get levoglucose if it is left polarized, and dextroglucose if it's right polarized. I hope this experiment is at least coming back to you, even though you may have ignored it in high school. Is the same concept. Instead of having to filter light, in radio waves, we can just create whatever polarization we want. So we essentially have a source. I'm going to draw it out. And this is going into how a radar is made. But you have a source, you have a delay line, you have another delay line, and you have a second delay line here to adjust, right? If a horizontally polarized wave is emitted from an antenna, which it can be, and it is, right? I can then phase shift it in this delay line. So I can say, hey, instead of going at this time, you're now going to go 45 degrees offset from when you were before, right? And this is very easy to do with radar waves, or radio waves, I should say. You can then combine it with a differently phase shifted version of that same wave to form a circularly polarized wave, right? So you have horizontal, you shifted it by 45. Now the wave is sort of like this. You're combining it with another wave that is sort of like this. What you get is circular polarization. And any combination of thereof. I'm just demonstrating like the hardest case. The easiest case is, okay, switch this off completely. You have H. Set this to 90 degrees, you have V, right? So there's ways of playing around with polarizations of radar, and it's much easier. You can do it electronically. You can do it sort of pulse to pulse, right? And that's where the trick comes in. So for most modern radar systems that are polarized, what you will do is you will switch your radar to be H. So in this case, I've used X and Y to be very general. But for example, this will be H. You'll transmit to the ground. When it comes back, you will receive H, H, right? So let's say you transmitted it, it came back. You are already at H configuration, you'll receive that. And you can have a second antenna to receive HV, right? And so on and so forth till you get to the next point where you've transmitted V, in this case, receive VH and VV. So now what you can do for a single pixel on the ground, right? So as we say bands in optical image, we can say we have 4 polarizations that can be arranged in something called a Sinclair matrix. Don't worry too much about the math. But here this is basically SHH, SHV, and so on and so forth, right? So this matrix now contains scattering information from whatever you hit on the ground with a great amount of detail. You have what happens if I send a H, what happens if I send a V, what happens in the cross pole. So you have a lot of information about this ground compared to just measuring it with a radar. Another thing you have to keep in mind, all radar images are complex. So this has a plus IB term, which means it has a phase, right? And you can use phase comparisons to find small shifts in radar images or between two images. So that is called interferometric SAR. We won't get into too much detail now, but bear in mind, like this is a very information dense data set, right? And anytime you think or hear of an information dense data set, what you should think of is, this means human beings can't easily parse this information, which is true, right? You cannot easily see a 4 by 4 matrix and come to a conclusion. For human beings, we have to come up with some visualization strategies like this, where you see the color coding is done. This color coding is done based on these the H and the V images. So the HH is given blue, VV is given red, and HV is given green, which roughly corresponds to single bounce, double bounce, and forest, because that's how it is known to come back, right? This is in contrast to like a X-band radar image that you're seeing earlier, where yeah, it has a very high resolution, but not more information than that, right? You just have the detected image information. So just to give some ideas of what you can do with polarimetric SAR, for example, and I'm going to be very brief because we want to focus more on the machine learning part, not on the physics part. But my message here will always be understanding the physics helps you make better machine learning algorithms. So you have this matrix that we have discovered last, right? And I have this image that is taken by JPL UAV SAR. Again, this data is free. You can all download it. Just search UAV SAR, right? Now, if you notice, this area I'm drawing in green looks very different from this area, even though they are the same region. Can somebody guess why that is happening? Let's see. Take any guess. Any wild guess in the chat is fine. Okay. Any guess? No guesses. Okay. In interest of time, I'll sort of tell you. The radar was flying in this direction. You hit this at the bore site. Whereas when you hit this part of the area, you hit this at a target because of that slope, which means any change sort of in the angle of the building can cause a big change in the radar. And I want you to remember this fact, right? So basically, if you are not hitting a target dead on, you're not getting all of the radar energy back. And if you're not getting all of the radar energy back, you assume it was scattered away, like in trees, right? So in trees, it is very common for the energy to be scattered back. So that's why we color coded it green, which is clearly a mistake because it was still an urban area, just rotated, right? I'm going to go to the next slide and we can come back to this sort of visualization. Here also, you'll see something interesting. Some parts of this forest look different from other parts of this forest. Can anybody take a guess as to what has happened? Again, I'll look at the chat. Any guesses? Any guesses? No. Okay. There was a forest fire here, right? So as the tree leaves got burnt, you're getting more surface scattering, which is blue, and less volume scattering because the tree burnt away. So as you can see, like there is a lot of information in this image, even from the visualization I'm showing you, which is, you know, an information lossy way of representing this data. And you can see how this image is made sort of in the left with the math. But what this should tell you is there is a phenomenon on the ground. There was forest fire, right, in this area. And I can now remotely sense it with this radar technology. I can hence train an artificial algorithm to do the same thing, right? That should always be how your mind thinks. I feel like if you can see it with your eyes, elevation was a good guess, by the way. And I'm going to talk about, so the elevation changes in this area. So you can see there's a brightness difference, but this particular area was just forest fire. So you can see this is in the radar shadow, this is in the radar side. So because of the elevation, you have some brightness difference. But the color difference is purely because of forest fire. But that was a really good guess because that also contributes, right? So elevation and scattering volume will contribute. But I think what I want you to know from this slide, without looking at the complex math in the left, is that if you can detect a change with your human eyes, 9 times out of 10 you can train an algorithm to do exactly the same thing, like without worrying too much about it, right? So I'm going to sort of go ahead a little bit. I'm not going to talk about the motivation, but here is the idea. If you take your data that you had, right, HV, you can train something called like an autoencoder. This doesn't require labels. All it is doing is trying to mimic the image. And after that, you can train something called a classifier to finally say if this is urban or not. So as you saw, there's a very big problem with the radar line of sight, right? If something is at 45 degrees or something is at, by the way, I'm not keeping a good eye on the time. Will please let me know if we are over time. I know we are slightly over time, but I wanted to show off at least this application before we can take a quick pause.
Yes, yes, you can show it quickly, but next
Yeah.
speaker has arrived.
Oh, cool. Okay. I'll just go through this application and then we'll take a pause. And sorry, we don't have that much time for questions, but I hope you could ask it during. Right.
Yeah.
So if you see, there is an oriented area and a non-oriented. So if now I start simulating some targets, right? So some buildings, I rotate them 10 degrees, rotate them 10 other degrees, see what happens. I can now greatly enhance this neural network, right? So I have this database that I've trained, completely simulated. I have these unsupervised features that I learned from the image, and I can now go apply that. So you can see I have the image, I did the filtering as you do, then you rotate to another angle, rotate to another angle, so on and so forth, to create something very generalized, which is then given to an autoencoder. So here's the exact autoencoder. And this autoencoder now learns some representation. You can use that representation layer along with some more parameters from the image, statistical parameters that we don't have to discuss. But the main idea here is you can extract that same physics that you knew about from the image, and then you can use a classification. And just to show you, as you can see, as I artificially rotate this area, different parts of the image light up, showing that my physics-based assumption was successfully encoded in the neural network, right? And then we can go through this part where, like, of course, the feature representation for this should be different from that. And we can prove it is true. As we see, there is some very small training areas, the thing you see in red and green, which I knew for sure is urban, forest, and water. And it has gone and found the rest of the areas. And as you can see, like wherever even there is rotation, it's doing much better than before. And these are some details of it. You can see the airport, the terminal is classified, the area is classified. And we can sort of see a comparison, if you want, with like a typical classifier. So typical classifier that doesn't understand the physics of this situation will classify this as forest because it thinks, oh, the energy has gone away from me, it must mean nothing. But the classifier that does understand it will classify it with red, right? So this is just some more if you want to compare with other state of the art ones. But you can see again, physics derived classification definitely is superior. And it should not be a surprise, right, to all of us, because at the end of the day, I'm going to stop my screen share and just talk through the last parts. Like, this shouldn't be a surprise. If you can teach something physics, it can also understand machine learning. I know we were a little rushed in the end. I hope you don't have too many questions. If you do, please feel free to email me at this email. And of course, the slide deck has more, so I'm happy to send you the whole slide deck later. With that, I'll take a quick pause, and if you have a quick question, or we can.
Any questions from participants? Okay. Okay, thank you, Dr. Shaunak Desa, for encouraging us with your interactive and informative session and spending your time in spite of time zone differences and making the session wonderful even at 5 o'clock in the morning at your place. So now I request each one to please switch on the camera for a group photo with the speaker.
Good evening and welcome, Shivmon sir. Please switch on the camera for a group photo.
Oh, good evening.
Good evening.
All
Good
and
evening.
Shaunak Day. See you
Yeah.
after a long time. Yeah.
Sorry, my mic was muted. So many years.
Yeah. So many
I
years.
hope to see you in person soon, though.
Yeah. Certainly.
So, dear all, please switch on your camera for a group photo.
Okay, thank you.
Okay.
Thank you.
Thank you. Shaunak, you visit sometime?
Absolutely, sir. Absolutely.
Yes, visit us.
Yes.
You're doing good work at Capella. I know.
I'm still very regularly talking to both Rakesh and Anup, so I'll come
Rakesh
soon.
has left, it seems.
Yeah, I realized this January.
Yes, Anup is here. Okay.
Okay, thank you, sir.
Okay.
Thank you, Shaunak. Yes, you may proceed, Kyuti ma'am.
Okay.
So,
Good evening, one and all. I, Dr. Rashmi Kevte, Committee Member ATAL FDP RSAML 2023, is fortunate to present before you today's session to enrich you from a well-known academician from remote sensing field in India. Today, we have with us a learned expert from remote sensing area, Dr. Shiv Mohan Sir, specialist from microwave remote sensing for Earth and lunar surfaces, Gujarat, India, as our speaker. Dr. Shiv Mohan Sir has contributed toward microwave remote sensing applications development in India during his service at ISRO since 1978 to 2011. His research achievements encompass broad multi-thematic applications of microwave remote sensing for Earth resources, applications, and planetary sciences. He got an opportunity to work in various research projects from the global space agencies like NASA, DLR, JAXA, ESA, and ASI. He was the main architect of India's first RESAT utilization program, where he worked as a project detection model and in the definition of Chandrayaan 2 dual frequency SAR payload. He is also involved in future Venus mission. He has 320 research papers in journals and conferences and also guided 22 PG and 3 PhD dissertations. He is recipient of Indian National Remote Sensing Award 1995, Outstanding Reviewer Award from Elsewhere Netherlands in 2015. He is the first Indian scientist who received the prestigious Outstanding Service Award from IEEE GRSS in 2022. He also served as a visiting scientist at DLR, Germany during 1980 and 1981, and chief scientist HAR SAC, Haryana government during 1998 to 2001. In his tenure, Dr. Shiv Mohan Sir is presently visiting professor at CEPT University, Nirma University, and Gujarat University. Welcome, sir. Now I request Dr. Shiv Mohan Sir to continue with the session and address all the listeners with your expertise.
okay, thank you for nice introduction.
Thank
You
you.
kindly allow me to present. Okay, it shows now. I'll present it.
You may share now, sir.
Okay. Okay, good evening to all of you. And I'll share some of the results from some of the experiment, not all, which are relevant to you and relevant to the data analysis process that what SR can do and how we do the analysis and what is the physical basis of doing that and some of the experiences in machine learning process. SAR become immediately important to our country because this is the only sensor which allows us to see through the clouds. And you can see the clear cut image because the SAR works on the microwave frequency, and microwaves can penetrate through the clouds, and thus we get the clear picture even during the cloudy conditions. So that is one of the requirement of the country, that you not only uh, Rabi season, you also work for the many crops in the Kharif season, as well as we have to work for the disaster management related theme, like the floods and the other cyclone and so on, which are normally under the cloudy conditions. So that's how our country has initiated work in the micro remote sensing. A SAR sensor or radar sensor, it operates in a
Excuse me, sir. Could
yes.
it be in a presentation mode so that we can see it in large?
Yes, 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 yes. Is it okay?
Not yet, sir.
I have put in the presentation mode. Now it is should be okay. I am seeing in the presentation mode.
Here it is not shown. I think it is window or tab which is been shared.
Okay, window is shared, so I'll just again share in the PPT mode
Yes,
only.
plus because it is not visible.
Okay.
Sir, it is not yet shared.
Yeah, I know it's not shared, but tab and entire screen I do, it's not doing the that way. Only window it does.
Okay.
Because once I do window and then I put on the slideshow, it should show you the page.
The slideshow would be the second window, sir, in that case.
No, it's not doing on second. It's doing only on the first.
Okay, you may continue with the same, but please zoom out then in that case. So we
Okay.
could see. No issue.
Okay, I'll just do a bit trick.
Yeah.
That. But what about this? Is it clear? This picture?
Yeah, yeah. It is clear.
Okay. Okay. So I will just take care of the wherever smaller letter sizes there. Probably I may skip that. And but when I share with you the total slide, I will give you that one also.
Okay, sir. Okay, thank you.
Yeah, because the
Okay.
smaller has no meaning.
Yeah, yeah, yeah. Okay, fine.
Okay, so the SR sensor operates, one thing is in the side mode, that is different than what we see in the optical, which is the seeing just down to the earth. It looks towards an angle like this, and the different mode of acquiring the data, which is called strip mode, strip by strip, or it's a scan SAR, means you want to have a large swath, or a spotlight mode, that means the very high resolution radar. So whatsoever is the way of imaging important is what it measures. It measures the two things. One is the intensity of reflected signal, that means what we transmitted and what has come back. That is the intensity, and which is a picture form, like you see the here. I have the picture form. And other is it gives me the phase also. Phase means I have suppose transmitted this red color, a phase of my wave, and what I get is a blue color. That means there is a shift in the phase. So our instrument measures only phase this one, what is in the blue, which is a cycle, because it's a cyclic. Phase is 0 to 2 pi. So each 90 degree, you can give a color and you get this kind of number. This is my phase and this is my amplitude. So data is different than what we get. One is we don't get the phase in optical because that kind of coherent sensor are not existing. Radar is a coherent sensor, so that's how we could measure it. Phase absolute value has no meaning. You can see this picture. But when I compare with the transmitted signal like here red and what it comes back a blue one, so there is a phase difference between these two. And this phase difference has some meaning in our analysis. We will see what it is and how we use this phase information. Let us see the data. Data is a now two-dimensional distribution of intensity. That is what area I am imaging. One is called azimuthal direction, other is range direction, or across track or along track, whatsoever we can call. And my each this box is a element, that means ground resolution on the or resolution on the ground, which has a value here in amplitude and other has a phase value. So we, for a given data set, one equation, we have two kind of variables which are available to us for the analysis. So that's how the analysis becomes little complicated, because this image phase information, our eyes are not sensitive how to read the phase, so we have to use some mathematics. Other is important thing when we analyze SAR data, we have to look the different frequencies, because SAR works at different frequency and mostly are from X band to L band data is available nowadays. So you can see the when I use one of the band SAR from one of the satellites, suppose I'm using C band, and if I use same area for the some other frequency like L band, my data will be much different. One is because of the penetration. The data at the L band will penetrate more in comparison to C band in a medium. So some of the signal which is not coming from at L band may be seen as a at X band. So that's also other variable which we have to consider in the imaging mode. And this penetration depends on the wavelength what we see. This is the wavelength, which this is a penetration depth proportional to the wavelength. Now what happens when I use a L band kind of sensor, you can see that this black thing, that means signal is not coming back to my eye sensor, and this bright signal is interacting with something below this surface, and that's how that comes back to the sensor. So we are able to see some of the areas, black areas, which is at a where signal has gone at a deeper level, and bright area where signal has come back from the deeper level and returned to sensor. So thus we are able to see many things if we use the uh, some sensor at a lower band like L band or P band, something here. So the if same area, if I use X band or something else, I will not get this kind of information. So a common for a given area, you will see variability R because of what wavelength we are using, and phase value is different for L band and C band. So that's the number of phases will also cause a change in the your numbers what we are seeing in the. If I use many bands like C band, L band or P band for a given area, you can see my values are totally different. My digital number values are totally different at C band to P band. Here penetration is more in the soil layer, these colors. Here penetration is not existing. For the tree cover area, you can see the dark signal has penetrated, doesn't come back. That is why it is dark. And here in expand, it has not penetrated totally, but part of this. Where density of the tree cover is less, it penetrates. So the concern is that our interest should be first to what frequency we are working. And there is one more variable from the sensor side is the polarization. The radar waves are normally polarized, either H polarized or V polarized when we transmit. H means horizontal, this is the direction of polarization. You can see a plane, and vertical polarized means a direction in which our polarization vector is aligned. So when I transmit a H polarized wave, which is horizontal here, and I receive back both the component H and V. So this becomes HH and HV polarized. My data is called the HH and HV polarized. When I transmit a VV polarized wave, V polarized, then when I return back, I will get VV as well as VH. That means some of the polarization has been transformed to H, and some of the polarization could not transform to H polarization. So my ability to discriminate targets become easy with the help of these polarization vectors. Some of the targets changes the polarization state. Some of the targets they do not change the polarization state. So that's the thing in this, that the many things we can visualize by knowing the how much change in the polarization vector takes place. Earlier, we used to have only single polarization radar, but now it is going towards multi-polarization radar. And you can see in a given area, if we acquire data in all the four polarization, HH, VV, you can see there's a change in the intensity. This bright thing is not bright here because this target could not change H polarized wave to V. H polarized wave totally comes back, but V polarized wave doesn't come back. So we have to see what are the reasons for this, and accordingly our classification method has to be developed based on a physical basis or machine learning. It is slightly complicated today because some of the things we have done, I will just show where it works well. Now, one more characteristics of radar is it is a coherent sensor. So in a pixel, what happens? We have suppose it's a crop type of thing. Each each element in this crop returns back my wave in a coherent wave, and all these waves interfere among each other to give me a uh, constructive and destructive interference. Destructive means zero intensity, constructive means double intensity, whichever is coherently adding up or subtracting. So accordingly, we will have this kind of situation in the, so it's very highly noisy data, and noise is because of speckle nature, and which is a multiplicative noise. It is easy to uh, model this kind of thing to reduce the speckle noise. At the same time, the new algorithm with the machine learning technique, people have come with a noise data using synthetic data from the optical, and they synthesize the SAR data and add noise, different kind of noise, and some possibilities has been explored to minimize this noise, and which looks much smoother. So one process is that before analyzing, one has to do this process, and other processes you have to normalize with reference to some standard target. Suppose some standard target which reflects the intensity x0, and with reference to that, my all these digital number will be normalized so that I can compare day-to-day data. So this is called the calibration of my data. So these two becomes the important step before we go for the analysis of further data. Now, what happens on the ground when this wave comes on the ground? The different things happens. It interacts with the surface. Suppose this is my resolution cell. It interacts with the surface. It interacts with the vertical structure, which could be crop, which could be forest or anything. So if the signal penetrates into this is called a volume scatterer. If the signal is scattered with the surface only, this is called a surface scatterer. So these mechanisms depend on the which wavelength we are using and which polarization we are using. Accordingly, the intensity of the return signal will be varying. Now, if I consider a simple surface like this, which is very smooth here, with reference to wavelength, L band is at 21 centimeter and X band is at 3 centimeter. A surface at X band could be rough or smooth, but at L band that becomes smooth because wavelengths are much bigger, of about 1 feet type of thing. And here it is a X band is 3 centimeters, so very small variation in the surface will cause a rough surface scattering. So these two scattering makes my application differently in terms of physical basis. Now what happens in surface scattering, the dark wave interacts with the your material, it is the interface, and here it is air and here it is the material, is surface, earth surface. So when it interacts, so it is a specular reflection, so we don't get back any signal. As soon as surface is rough, scattering is in all the direction, and we get back some more signal in more than smooth surface. So what happens? All surfaces which are smooth will give me dark return, which are rough will give me bright return. As a consequence of this, I can now my put signal into information. That means when there is a specular reflection, that means no signal at a sensor, nothing is coming because everything is going in, all signal is going in some other direction. So it becomes a dark, and I can, in my agricultural field, all smooth surfaces. A smooth surface here means fields which are not plowed becomes dark, and fields which have been plowed give me surface scattering and diffuse scattering, and I get back signal which is more. So I am able to do the agricultural in season agricultural operation, that what is happening in the field, whether they are plowed. Plowed means all these will be going through, you can say all will be used for the agricultural activity, in season activity. That means these will be planted, and you have initial forecast from this kind of information. Before the seeds are sown, you can tell so much area will be used for the agricultural activity. So with this kind of thing, surface scattering model are used. One can use without model, or one can do the some sort of machine learning approaches. We will talk about that. And you can do the application like this: water surface detection, water spread, which means flood mapping, or flooding a cropland like paddy, because it's used in it, they just flood the surfaces, all the paddy fields. You can know that they're going to implant some agricultural crop there. So similarly, many land cover classes will be, you will find that they are smooth surfaces like the playground, open spaces, roads, runway. All these will be seen as a dark. And you can see the oil spill is also in the ocean. This ocean image, oil spill is also uh, dark because of the region that radar signal, when it comes, this portion acts as a smooth surface, and all signal is going in other direction and you don't get back. So it's easy to detect oil spill. Simple change detection technique one can use and find which are the area where oil spill is there, one of the. And similarly with change detection, one can find the water spread in a river system which is causing a flood, and also what are the uh, tank, irrigation tank, which are full of water. But the issue comes in the irrigation tanks. Uh, yeah, you can see this is my, if I take a large patch, all tanks are full. Here you can see, and I can monitor the change direction, uh, how much water is full year to year in a tank. Is full in 2019 because of heavy rainfall in this area, but 2018 it was not. Now, when we do this kind of thing, what happens that you can do when it is full, but at the border of this, you will see at land water interface, this doesn't give me a good information. That means that there will be always error when there is a at this interface. So one can use the machine learning technique. Here we have used it some random forest model, and with that we have found that it's able to give me better and repetitive information in a more correct manner in comparison to my only simple lidar images. So one can use, and this has a large scale with, for whole year we have tried this kind of models, machine learning models, and it works fine, and certainly a excellent way of utilizing the machine learning in this case, because they are very simple cases. Only problem comes at the interface, and if you are doing the mapping for a large area, suppose whole state or whole country, then that small error becomes a high because it's summed up at the nation level or state level, then total water quantity number becoming variable. Now other is okay, 10 more minutes. We'll talk about uh, second component, that is volume scattering component. And what volume scattering means, the signal comes on the ground, interacts with the canopy, and goes in this direction and also back direction. When canopy start growing, that means when crop start growing, your return signal will be keep on increasing. That means back scatter my increase with the days after transplantation. So this is the way we can do this analysis, uh, crop analysis using supervised learning method. But there are uh, some small kind of efforts we have put, that using some machine learning approaches, whether we can detect this kind of enhancement in the back scattering due to crop, and then it becomes easy for me to find the date of transplantation and date of maturity of a crop, which is much more useful. So with maximum likelihood or supervised classified, we have done this, but we want to go ahead with some of new machine learning algorithm. And same thing when we do with multiple band, our accuracies depends on the what frequency or polarization I am using, but we can think that my C band gives him best accuracy in comparison to X and L band. X band doesn't see to all the crop, but L band sees more than crop, so that's why error are there, but C band doesn't do it. Now let me uh, do one or two example on the model-based analysis. In the model, what we do, we try to relate with biomass. It is an example of the biomass with backscatter, that means calibrated radar return, and we try to see how biomass changes with backscatter, because when there is an increase in biomass, there is an increase in number of scatters present in that tree, and that causes a increase in the backscatter. So using this kind of empirical approach, one can invert and develop a biomass uh, biomass map of a area. So this is a quite exhaustive in terms of analysis technique and requires a lot of effort. Similar thing is through models, one can detect high soil moisture zones using multiple data set at a given band. So like blue, this is basically physical model, and which takes into account the kind of soil, kind of wetness, and also if there is a crop, then its effect on that crop is also analyzed to give this kind of surfaces. Now let me show you few examples before we finish. That the okay, what is the influence of polarization? When we see the polarized wave like this, when I transmit a polarized wave and receive vertical polarized or cross polarization, as soon as there is a tree cover, there is enhancement in the backscatter due to cross polarized signal, and we are able to see vegetation very accurately in comparison to linear polarized signal. So immediately one start using the cross polarized signal for the identification of the crop area or vegetated area. Here the only polarization status we have seen. What should be the best polarization of crop or vegetation studies? And our studies indicate that if we use all the three polarization, our accuracies are of the order of 92% in the typical cases. Now there are ways by which we can decompose the return signal into a number of components, that is matrix. We can decompose into surface scattering, double bounce, and the volume scattering. It gives us a fairly good idea to find how much is the vegetation, green color, how much is the man-made target, and how much is the surface, like water body. Now, when we do it year to year, then what happens? There is a change in land cover. So here the vegetation is converted into double bounce, that means human settlement. So one can do that kind of study just by decomposing a signal in multiple years, and similarly water body, its area is changing here and here. So these are some of the standard polarimetric method where we decompose data into a number of bands and try to do the land cover changes in the area using micro data set. Some land cover changes are there at different bands. Now I'll give you one example on the lunar surface where you may be knowing India was a country who detected water ice on the lunar surface. The two sensors, one is the hyperspectral, otherwise the micro radar. So here that time we connected with the Indian, not in Chandrayaan-1 SAR data, and identified some of the craters which were having water ice. Now using machine learning, one of the models, support vector machine, we have used this, and here with this model, we could detect, I think, 14 craters more than the what we did with the conventional method. Conventional method utilize the polarization properties of the return wave, but here it is doesn't use the polarization. It uses a very stable, you can say, input. That means supervised learning is done very carefully with the known data set, and then algorithm is applied over large area to get to have a assessment how good it is in the detecting a new areas with water ice. So with this, my time is over, or still times, yeah, it's over. So some more thing, okay, all right. So now there are two ways. One is the standard procedure, that means pixel-based analysis, in which we can use the uh, image processing method for the data analysis. Other is physical-based method where we use the uh, you can say the process by which the signal is coming back. Third is knowledge-based classifier. Of course, it's a part of digital image processing. Then model-based analysis is one approach where we get more based on the theoretical model, and we get the information about the surface area. Then machine learning is relatively new approaches people are trying so that it can be scaled down at a larger scale, and we can have a more standardized, but it takes some time because the input variables are not constant even in a given area. and they keep on changing. So which depends on the input, how accurately we can do. But lunar surface, it is rather more easy because my input doesn't change. Even today, if I collect the data and I collect after 10 years, there is no change because there is no human activity or any other activity on the lunar surface which disturbs the surface except the crater mechanism by which the new craters are formed. So these are some of the analysis technique and many applications we can talk about using this, which utilizes the full vector nature of the wave. That means amplitude, phase, and polarization. And efforts are more towards quantitative and accurate information, so that uh, yeah, that's what is the requirement, more accurate information, and one can rely on this kind of data set. So thank you. I am closing at right time, 8:45. So if you have any questions, you can ask.
Any questions from the participants?
Sir, from my side, one question is there.
Yes.
If we want to identify the crop, and suppose
Yes.
there are two types of crop, and the features of two crops are similar, in that case, how can we identify both, or how can we classify that type of a crop?
No. Oh, see, feature of the two crops will be different in one polarization. We have four measurement,
Okay.
and it is assumed that any of the polarization we will get it differentiate.
Okay.
Suppose we are not able to do it,
Huh.
then also in the temporal rate of change of increase in the
Okay.
vegetation biomass in the two crop will be always different.
Yeah, yeah.
Crop growth is not same in all the crops. So
Okay.
we do one more dimension, the time domain.
Okay.
So it helps us to resolve that problem.
Okay. Thanks.
Yeah.
Thank you, sir. Thank you, Dr. Shiv Mohan, sir, for encouraging us with your wonderful session. I assure you that many of us are inspired and will take remote sensing as an opportunity for the research here henceforth.
Yes, it will be interesting because I am also from IEEE side. We have recently started a virtual lab where we can provide training on the micro remote sensing also. Practical part.
Thank you,
Okay.
sir.
Theory anyway now everybody understands. So if somebody want to do practice on the uh, free software we use, and it is possible.
Yes.
So, could you, sir, provide the link for that VLab? Because we are having the MIC, microwave integrated circuits and other related courses, as well as the remote sensing course for
Okay, GLab
undergraduates.
is I am the coordinator of that, or rather
Okay.
initiator of that.
Oh,
Currently, I am looking after. So it is day after tomorrow. It will be demo, and then this February we are starting. You can write who wants and how many days. It will be open 2 p.m. to 9 p.m. 5 days a week.
okay.
Okay. Okay.
It's not whole day. 5 days a week, 2 p.m. to 9 p.m. 7 hours.
Okay.
Yeah.
Okay, sir.
So you can connect with me, but only it is facility is available to members of IEEE Geoscience Remote Sensing Society.
Okay. It is not for IEEE only members
No,
because we are
one has
having
to be.
IEEE chapter at our institute.
You have IEEE
Yeah,
chapter.
student branch is
So
there in our.
student, what they should do, they should become member of GRSS because there is no charge.
Yeah.
If somebody is member of IEEE, it's easy for him.
Hmm.
He takes the GRSS membership, and I think it is free of cost
Hmm.
for
Hmm.
IEEE member. One can check, but if there is a cost, $1 or $2 or $3, not much.
Okay, so that VLab is available for IEEE members and GRSS members. So
Only GRSS
only
member,
GRSS.
IEEE GRSS.
Okay.
So they have to raise that requirement to me, and I will be able to provide because we have four uh, four virtual machine with 16 GB RAM and disk space to individual could be 202 GB or something like that.
And which is the simulation tool?
No, it's not. Presently it's a analysis tool.
Okay.
SNAP is the tool. Not ArcGIS, QGIS is there. Uh, these two tools for the remote sensing data analysis, which are widely used. And any other free tool, if somebody want, that can also be added in that.
Okay.
Somebody has some tool which is freely available, it can always be added on that.
Okay. Okay. Thank you. Thank you so much, sir.
Thank you, sir. I request all the participants, please switch on the camera for a group photo with the speaker.
Okay.
Just a minute. I will take one more.
Okay.
Okay, done. Thank you.
Okay.
Thank you once again, sir,
Okay.
for
Thanks
your
a lot.
valuable inputs and sparing time in spite of busy schedule at this odd hours.
Sir, we are having with we are having with us Dr. Milind Mushrif, who is coordinator for this faculty development program
Okay. Okay. Yes.
from our department.
Nice to see you.
Mushrif sir, please over to you.
Yeah. Sir, your talk was very inspiring, very informative, and I think participants are very much benefited from your talk, and in future also we would like to have interaction with you, and if possible explore some research areas. We have many faculty members who are actually working with MRSAT. So,
Yeah.
uh, yeah. So we would like to have more interaction, more fruitful interaction with you. And your talk was very, very informative and very wonderful.
Yeah. Nice interaction with MRSEC because they are the right kind of people whose hands are fully in that remote
Yes,
sensing.
yes, yes.
It's nicely you're attached to the right place.
So many of our students are also doing their internship with MRSAT.
Yeah, they can do
Yeah.
really. Yeah.
Thank you, sir.
Okay, bye.
Yeah.
Now, anything more or it's over?
No, sir, it's over. Thank
Okay.
you. Thank you so much.
Okay. Okay,
Dear
then
part,
bye.
yes.
So should I leave now?
Yes, sir, please.
Okay.
Thank you so much
Thank
for
you. Bye.
sparing the time. Yeah. Dear participant, tomorrow we will meet at 7 p.m. for the another two sessions in the this particular week in virtual mode only. Please fill the attendance form. The link is shared in the chat box.